Let me share my screen. Okay. Yeah, I think it's 3 p.m. So we can start with today's doubt solving session. Let me check the recording. Yeah, recording is fine. Okay, guys. So right now the we are in the currently week 7. We have seen the all the concept that has been covered in this particular week, and we'll try to solve few questions based on them. Those questions will be in such a way that you will be able to solve the assignment question, which will be given in the week 7. Okay. Yeah. Uh, yeah. Can you guys? Yeah. Pranav sir. Okay, yeah, let me mute you. Uh, okay. Yeah. It's muted. Okay. Let's get started with the week 7 content. So the list of the topic that has been covered in the week 7 has been given below. So we have discussed about the ball milling. We discussed about the high energy ball milling, and we seen that how we can use these things, like under what condition one should use ball milling, or under what condition one should use high energy ball milling, which is also known as planetary ball milling. Okay. Then we have understand about the purity of the nano composite which we prepared by the ball milling process. Like we are aware that the material, if we are ball milling any particular material, let us say any particular powder, let us say Zeta-2, zirconia, it might be very well possible that the wall of the container in which we are milling the things, and the medium in which we put it, let us say any ball, let us say tungsten carbide ball we put, so that it can help in the grinding of the material of the zirconia. So now it is very well possible that the wall of the container, or or the ball that is tungsten carbide ball, the material from that those things can get into the powder, and it will decrease its purity. So from that aspect also we have seen that uh, how the nano composite that we prepared using the ball milling gonna affect. Next we learn about the superparamagnetism, that we keep on deforming, that we keep on decreasing the size of the material which was ferromagnetic in the nature. When we go to the nanoscale, that transition from the ferroelectric to the super paramagnetic occur, and how it is useful to us, that those factor has been discussed. We discuss about the type of the CNTs. Okay, that's sharpen one and the coiled one. We have discussed both of them, and then we discuss the impact of the structure on the damping property. Like we have seen two types of CNT over here, and under what condition we will use one CNT, and under what condition we'll use another CNT based upon the damping properties. For the damping properties, okay. So those are the things that has been covered in the week 7. Okay. So before I go ahead, let me know, is there any doubt in this particular concept that we have learned in the lectures of week 7? Okay. Since there is no, let's move ahead. Let's go to the question number 1. So now the question is telling that what is the main purpose of the ball mill? Okay. So again we have to think about the main, that is primary purpose of the ball milling. And let me tell you, the only one answer is correct in this particular thing. So one is to separate the different material based on the size. Is this the purpose of the ball milling? That we have to separate the materials. We are having the mixture of two material and we want to separate them. Is this what ball milling will do? This is option number 1. Option number 2, to mix the material together. This is the one. Like we are having material A, we are having material B, and we want to mix them. This is another. Okay. Third one, to break down, that is grind material into the smaller particle. So now the third one is telling that okay, we are having the material which is having the higher grain size or particle size. Now we want to break it into the two different size. We need to decrease the size. We need to grind it down. Okay, this is the main. This is the one of the purpose. Okay. Now the D, to create the flat sheet of the material. Is it? Are we creating the flat sheet out of the material? That is, they are telling that okay, we will get a material having this particular type of sheets. So now, what do you think? What is your opinion on this? Let me say that yeah, there is a two answers are correct, but again we'll go to the main option, that which one is the primary purpose of the ball mill. So here we can see that when we are milling, yeah. So as per the pronouncer, what he's telling that to break down the material into the smaller size. That is the purpose of the. That is why we are calling it to the mill. Okay, and so the ball milling, the main purpose is to do this. Also, one can say that I use to mix the two powder in my lab. Then it should be the to mix the material together. That is also the correct option. Okay. So if it is MSQ type, then the answer will be B and C. But if it is a MCQ, that is only one answer is correct. Then I will go with the option C. So the main purpose of the ball mill is to decrease the size. Now let us say I borrowed some material from let us say Sigma Altish, and the particle size is for 60 micrometer. Now my guide told me to refine it and make it to the nanoscale. Let us say around 100 nanometers. So under those conditions, I will use this the ball milling process. Okay. So I have this question number one is clear. So the main purpose of the ball mill is to mill down the particles, decrease their size. Let me know if there is any doubt in this question. Question number one. If there is no, let's move to the next question. Now this question number two is again extremely easy one. How does a ball mill work? That is a question. By crushing the material between the two roller, like they are telling that okay, we are having the two rollers, and in that we are keeping the powder, we are keeping our sample, let's say something of this particular size, and now from here we are getting the particle of smaller size. First one, by using the rotating ball to hit and break down the material. Okay, now it is telling that okay, we have the rotating ball, and now what it will do, it will hit our material. It is this is our material, and now this material it will break it down. The second option. Okay. Third is telling that by forcing the material through the screen with a smaller hole. That is, they are telling okay, we are having the net. The net will be having some size to that. The whole size will be there, and on that net we'll put our powder. And now whatever we'll get from the smaller size, we will be taking that okay, this is the ball milling. Option D, by applying the high voltage to break down the material. So what do you think? What is your opinion that among this, which one is the correct option for the ball milling? A, B, C, or D? Okay. So here we can see that the we will take in ball milling, what we do, we'll take a container. In that we put our balls. It is a zirconia or tungsten carbide ball, and we'll also put the our powder in it. We'll close this container and we rotate it by a certain axis. And so this zirconia ball or tungsten carbide ball, it will hit the powder and it will break it down. So rotating balls, we are having the rotating balls, and it hit down and breaking down the material particles. Okay. So the option B is the correct option in this particular question, question number two. Okay. If there is any doubt, please let me know. If not, let's move to the next question, question number three. So here, what are the some forces involved in the grinding process of a ball milling? Okay, so we are doing that particular ball mill. Okay, now we are rotating it down. Now, what are the forces that is acting on this particular in this entire process? The first one is telling that only friction force is acting. Second is gravity, friction, and centrifugal force. All of them are working. Only centrifugal force is working. And D, only the chemical reactions are involved. Yeah. So as per the pronunciation is telling that it's option B is the correct option, right? So what we are doing, let us say we are having this ball mill. About this axis, it is rotating. Okay. So now what is happening that this particular balls, let us say, they are going up due to the centrifugal action, and now it is coming down and strike the material and is breaking it down. What are the forces involved? This ball is over here. Gravitational force is pulling it down, mg. Centrifugal force is moving it forward, mv square by r. And when it is striking the powder, the friction force and the impact forces are involved. So with that, we can say gravitational, friction, and centrifugal, all of them are working over here. So with that, option B is the correct option. Okay. Let me know if there is any doubt in this question. If not, then let's move ahead to the next question, question number 4. Now, what is? First of all, the word is. So the only one answer is correct. What is the limitation of the ball mill for grinding very fine particles? Okay. Now we want to grind this our particular material, let's say having 60 micrometer of size, and we want to break it down to the very fine, let's say 100 nanometer. Okay. Now, what are the limitations of this particular ball milling process? Why we let me tell you that we won't be able to do that. Option D: the materials become too sticky and clog the mill. Okay, that can be one of the options that okay they are agglomerating with each other. Right. Let's see the other options also. The ball wear down too quickly. See, we know that ball will wear down, but adding the word that too quickly will be problematic. Let me tell you, zirconia ball if we are using the zirconia ball for the milling. In most of the application, in most of the mixing of the powder, we use the zirconia ball. One can use this multiple time. Okay, so it will wear down, but not to very large extent. So option 1 is incorrect. The cylinder cannot rotate fast enough. That is again the incorrect one because it is in our the rpm is in our hand. We can do as per the we can increase the speed as per we want. Third option, fine particle can float in the air, okay, and avoid being hitting by the balls. So now this is the one. See, we know that when we are having the particle, it's going to the nanoscale. The effect of gravity is not that much once we keep on defining the particle size. So now what is happening? They are being in the container entirely. So our container was initially was like this, let us say, and powder is coming from here, and let us say this is a ball. It climb all the way from here to here. Now it want to strike the powder, but powders are not there. Powders are everywhere, and that's why since it is in the air, it's floating in the air. It's without because it's not having the effect of the gravity to larger extent. That's why it's being avoided. The heat is avoided. So option C is the correct option. And let's see D. The material become too sticky and clog the mill. So now here it can be also this is also the right answer. But to the larger extent we can say that option C is right one. Option D is telling that okay they will stick with each other. They will let's say I went to the finer size. Now what is happening? They are agglomerating with each other and they are forming something little bit bigger size. This is also the right answer. If instead of is there should be are, then we could have chosen both of them. But since we have to select only one option, we will select the primary reason, that is option C. Okay. This thing has been discussed in the class that we cannot use the ball milling to refine the powder and go to the very fine level. Okay, and that is the reason why we cannot use the ball mill over here. We'll go with the planetary ball milling, which is also known as the high energy ball milling process. Okay, with that we have solved this question number 4. If there is any doubt, please let me know. Okay, since there is no, let's move to the next question, question number 5. Now this question is quite easy. Okay, so now they are telling that what will happen when the RPM of the roller is too high in the ball mill. Okay, now we are keep on increasing the speed. We are keeping we are it's very high. Let us say. So now the ball grind more effectively. The grinding media break down. The centrifugal force keep the ball stuck to the wall, preventing them from falling. And the D, the material become too sticky and clog the mill. Yeah, the pronunciation is telling that the option C is the right answer, and that is yeah. So we can see that if I'm having the ball and let us say powder also, and I increase this particular speed to the very large extent, what will happen? Like we have seen the Deadpool, right? That one. In that, what happened that the car keep on rotating onto the wall. In the same manner, if we increase the speed to the very large extent, due to the this mv square by r will dominate over mg, and it won't let our ball or our particle to strike down. Instead, it will just keep on rotating over here, and that's why option C is the right answer. So with that, we have solved this question number 5 also. If there is any doubt, let me know. Or else, let's move to the next question, question number 6. Now, we have seen the concept of the ultrasonification, and in conjunction with the ball mill, when we use like we did the ball milling, and now we ultrasonicated it. First one, increase the grinding speed. Second, improve the dispersion of the nanoscale material. Third one, cool down the grinding chamber. And fourth one, remove impurity from the sample. Now, in the class, we have seen that. Let us say I am having some. Let's say this is a polymer matrix, and in that, our nanoparticles are somewhere. Let's say carbon nanotube. It disperses something like this. Now, from here, if I want to disperse them quite finely, like instead of like this, if I want to disperse them in this particular manner, in the homogeneous manner, I don't want them to coagulate with each other. In that condition, I will use ultrasonication. What ultrasonication will do? It will produce the bubbles, okay, at a very high speed, and locally it can once it collapse now. That time it can have a very high temperature and high pressure also, and with that will facilitate to move from here to here, and we can get the more homogeneous distribution of the nanoscale materials within the matrix. Okay, so this can be done by ultrasonification. So with that, we can see that the option B is the right answer over here. I not did much in that. I just pick up this question from the lecture, the concept which we have learned. As it is this particular sentence, you will find that it is speak by our professor. Okay. If there is any doubt, please let me know. Meanwhile, let's move to the next question. Question number 7. Now, see this. Now, this the question is saying that XRD pattern is used in the ball milling too. Okay, I had a material. It is a 60 micrometer size. I did is XRD. Now, I put it in the ball milling for 1 hour. Something might have happened, particle size. Now I did the XRD of this. Now again I put it in the ball milling for 1 hour, and I got something, some particle size. Now I did the XRD of this. Why I am doing the XRD? What is the reason for that over here? That is something which we want to answer. Measure the purity of the material. Second, determine the size of the particle being around. Control the speed of the ball mill. Separate the ground material from the ball. Okay. So what do you think? What is the correct answer? Whether we should go with the purity of the material, or we decide the size of the particle, that is crystallite size. Okay, these are the options that is available to us. Now, what we know that, let's say I do the XRD of this. Initial material was looking something like this, the XRD pattern of that. Now, after 1 hour, we are seeing that it will look something like this. The peak has got broader. Now, after 2 hours, okay, after 2 hours, the peak will. I'm just exaggerating the things. It will look like that. Okay. So what now we need to answer that what this particular broadening information will give us. Okay. Whether since we know that XRD pattern how they are changing. Now we want to answer that what it is. Like if broadening is happening, if more broadening is there, what information will it give? Will it give all the purity of the material, or the particle size, crystallite size, or the speed of the ball mill? Those things. Okay. And we are aware that we have learned in the lecture that if the broadening is keep on changing, that it means that the crystallite size, yeah, the option B, yes, the option B is the right answer over here. That the particle size will keep on decreasing. Okay, so this was 0 hour, 1 hour, and 2 hour, and we have seen that the broadening is keep on going. And the reason behind that is that the particles, which was let us say of this particular size, it has break down into the smaller one, and it further break down into the again smaller ones. And with that, we have solved this question. Okay, let's move to the next question. Question number 8. Now, now this question is a concept which we have learned in the class. Like, let's read it. Why do doctors prescribe medicine to be taken at the specific interval of time? And see, when we go to the doctor, they say that okay, take it in the morning, then go with the afternoon, and in night you take. Okay, there is a certain type of interval we can say that okay, around 6 hours, and from between this also 6 hours. Now, what is the reason behind that? Why doctor said that okay, take it at 6 a.m., then 12, then again in night? Hey, to maintain the overloading the digestive system. Okay, so they are telling that okay, if they doesn't specify the time, then it will if we eat medicine, it will overload the digestive system. Second, to maintain the steady concentration of the medicine in the body. Okay, so that in that the concentration of the medicine in the body should be the maintain some steady level, it should be there. Third, to prevent the medicine from interacting with the food. Okay, so they are telling that okay, the food and medicine should not interact. Okay, so to prevent that, this particular time has been preferred to ensure the patient remember to take the medicine. No, the last answer is obviously not the right answer, because they are telling that okay, take at this particular time, take at this particular time, take at this particular time, and this time they specify because so that the patient shouldn't forget that. Now, what we have learned in the class that whenever we consume some medicine, let's say this is a concentration, this is the time. Whenever we are taking some medicine, instantly let us say right now we at this particular time we took medicine. The concentration of the medicine will be higher in that particular time. Then it will keep on decreasing. Now it will go to the certain level. Now let us say I went to the dentist and he did something to my teeth, and because of which it is paining. So I took one painkiller. Now I can see that okay, now I am relieved. But after a while, what will happen that the pain will again start coming. The reason behind that is that this concentration of the medicine has gone down to a certain level. If it is above this particular level, then the I won't feel any pain. So now again at this particular time, what we have to do, I will take one more medicine and the concentration will go high. Now again after a while it will start decreasing, and then again I will take one more medicine and the concentration will go high again, and this cycle will keep on repeating. So the interval which doctors specify for the medicine, it is so that the concentration of the this particular medicine will be maintained in our body, and so that we won't feel pain, or maybe for other some reason, whatever it will be. And so with that, option B is the right answer. Okay. So from next time onward, whenever doctor said that take medicine at this particular time, just go ahead and go ahead with that particular time. Okay. Okay. With that, we'll solve this question, question number 8. If there is any doubt, please let me know. If not, then let's move to the next question. Now, there is some other new concept that the time release tablets are designed to. So, dissolve quickly in the body, release the medicine gradually, target specific organ for the treatment, prevent the medicine from interacting with the other drugs. See, we take the medicine. Let us say this is a one particular medicine we are having with us. Now, sometime what happened that let us say this is a painkiller. If we are not feeling very like it's not paining a lot, but still we want to get rid of it, what we do, we just break the medicine in two parts and we consume half of it. Okay, so that our concentration of the medicine should not be very high. We do like that. Sometime it is not preferred for a time. Let me tell you that it's not preferred. The reason behind that, let us see the cost cross section of this particular medicine. It will look something like this. The inside layer, then outside layer compared to that, and the layer which is next to that. All these three layers, let us say the medicine is composed of the three layers. All these three layers will be having the different concentration of the drugs in within them, which is designed for some particular the way to for it to get dissolved. Okay, so one shouldn't take the medicine like this. We have to consume the medicine entirely. Okay, now uh, dissolve quickly in the body. We don't want our medicine to dissolve very quickly. We want to, if it is dissolved very quickly, what will happen that the concentration will go high suddenly, it will go back, it got dissolved. But if it is dissolved gradually, then that particular level of concentration can be maintained. So with that, we want to release the medicine gradually. So the medicine are designed in such a way that with the time the effect of it will last for the very long time. Okay, so the option B here is the right answer. If there is any doubt in this question, please let me know. If not, then let's move ahead to the next question, question number 10. Uh, Now, this question we all can answer together. Okay. The magnetic material are classified based on their response to an applied magnetic field. Okay. So let's say I'm applying some magnetic field. I made one coil. I'm passing current through it. I made the field over here. Now I'm putting my material which I want to test. I put my material. Now it can be para, it can be diamagnetic, it can be ferromagnetic. Which of the following materials shows the strongest response? Now we want to know that among this, which one will show the strongest response to the this particular magnetic field that we have applied. So what do you think? What is your opinion on that? Is para, di, or ferro? A, B, or C? Which one will show the highest magnetization? See, we have learned this thing better in the class that if H is the applied field, magnetic field strength, and we are getting B, magnetic field over here, we will see that if this is the response in the vacuum, so below that will be response of the diamagnetic material. Just above it will be the para, and the highest it will go very steeply. It will be the ferromagnetic, right? So with that, we can say the option C is the right answer because if I apply the small amount of magnetic field also, it will show the high jump in the response. While for the paramagnetic, the response is very, even though it is in the positive side, it will add to it. But still, this response, the extent, the intensity of the response is quite low. While for the diamagnetic, it will oppose this particular field, the applied field. Okay, H. So with that, we can see that the ferromagnetic material is the one which will show the strongest response. Okay, let me know if there is any doubt in this particular question, question number 10. If not, then let's move to the next question, question number 11. Yeah, yeah, we were on the question number 11. So when the magnetic field is applied to the ferromagnetic material and then removed, okay, H and B, we are applying the magnetic field to the ferromagnetic material, we know that it will show the very high response and it will go to some value. Now we removed it, it will go back to certain level. Even though magnetic field is zero, let us say, still it will show some value. Okay, the material retains a magnetism, that is what they are saying. Okay, magnetism. Instead of B, we can plot M also. Not the pattern will look same. The pattern of the hysteresis curve will look similar type. Okay, so this phenomena is called, so okay, this particular thing which is left over, even though we remove the magnetic field. What this phenomena called? Remnants, coercivity, superparamagnetism, or diamagnetism. What are these particular things? Okay, so what do you think? What is your opinion on that? That we have learned in the class that whether it will be remnants, coercivity, superparamagnetism, and diamagnetism. So we are aware that this leftover part is known as the remnants. Remnants, the word itself is that it's leftover. Now, if I want to make, right answer for this particular thing is option E. So now if I want to remove this particular magnetization which was there in my material, now I want to make it as it was before. What I will do, I will apply the magnetic field in opposite direction and will make it to the point till it becomes the B value. The magnetization will become zero. And this is known as the coercivity. Okay. And with that we have solved this question by 11. If there is any doubt, please let me know. If not, let's move ahead to the next question, question number 12. Now, superparamagnetism. We have learned this concept in the class. Okay. So here, huh, superparamagnetism is a property observed in the material with large grain size, nanoscale grain size, high electrical conductivity, low melting point. So they are talking about the superparamagnetism. We have learned that if I take the ferromagnetic material, that is something of micrometer size it will be having. If I break it down and make it to be the nanoscale, and it might be possible that due to this particular breakdown, now what will happen that the paramagnetic nature will change to the superparamagnetic. What is superparamagnetic? What is paramagnetic first of all? So what paramagnetic will do? Let's we are right now we are only talking about the paramagnetic. I am applying the field H, and in response to that we are getting some B. I applied it. It came over here. Let us say to certain value of B. I applied the H. Some certain value of B I observed. I removed the H. I removed it, and now I am going back to the 0. Again I applied, it will go to the some value, then again it will go to the 0. While in the ferromagnetic we have seen that if I applied the magnetic field strength sum, and then I make it 0, the externally applied field, still it is showing some value. While in the paramagnetic this switching was quite easy. While in the ferromagnetic this switching is quite like it will show some value. It won't be 0. Now this is where come the super paramagnetic, that now paramagnetic was showing the low value but ferromagnetic was showing the high value, but the paramagnetic was easy to switch from 1 to 0, but here it is difficult to switch. Super paramagnetic is something which show the high strength just like the ferromagnetic material, but it is very easy to switch. So now here, from here I applied the field strength externally field, and then from here if I make it 0, if I make h to 0, it will again go back to over here. So it is showing the nature of both ferromagnetic as well as the paramagnetic. Okay, and that is why that is the specialty of this super paramagnetic material. So with that we know that it can only be accomplished when the grain size is to the nanoscale level. So with that we can see the option B is the right option. Okay, so we have solved this question number 12. If there is any doubt in this question, please let me know. Okay, since there is no doubt, let's move to the next question, question number 13. Now, this is the question the concept of this question, we just answered it. Indirectly, we answered this question number 13 and the question number 12 itself. The question is telling that superparamagnetic material exhibit behavior similar to which of the following? Okay, so we whether it's a diamagnetic type or ferromagnetic or paramagnetic or ferro and para. This is the question. That we are having the super paramagnetic with us, and we want to know that whether it's diamagnetic, ferromagnetic, or paramagnetic. We are aware that it is a combination of the ferro, which is dedicated toward the strength, that is a high strength, while the switching is just like the paramagnetic for the switching. That is from the certain high field of B directly to the zero when the H has moved from some value of S to the zero. The switching is quite fast. Okay, so we are aware that it is a combination of the ferro and para. So super paramagnetic is a combination of both of them. Okay, so with that we have answered this question number 13. The right answer is option D. Okay, let's move to the next question. Question number 14. The potential use of the super paramagnetic material in drug delivery. Okay, see, we have prepared some super paramagnetic material. It is showing the switching and all, like easy to switch and having the high field also. Like it will give the good magnetization compared to the other paramagnetic materials. Now, what is the application of it? So we have used this in the drug delivery system. Now, why it is so? It can easily absorb by the body. Third, they can switch on and off when the magnetic field for the controlled drugs release. This is the B option. They are the highly resistant toward the degradation. Is it that they will not degrade? D. They are all naturally occurring material. Is super paramagnetic is a naturally occurring material? They are saying that. They can easily absorb by the body. This is the option. One of the most correct answer among this is option B. That if I applied the magnetic field, it can switch on. I can switch on its particular property of super paramagnetism. And if I turn off the particular field, it can switch off. Like we can directly make it zero. And in that particular manner, we can do the controlled drug release system. Okay. So let us say I'm having particular powder with me, and I consume this particular powder. Now, a doctor with the application of the magnetic field, and they can control this drug releasing system. They can enhance it with the help of the magnetic field applied, and they can also degrade its particular absorption. Okay, so in another way, they can control the drug release just by switching on and off the magnetic field. Okay, so with that, we have answered this question number 14. Okay, if there is any doubt, let me know. Okay, since there is no doubt, let's move to the next question. Now, this question is being answered in the class in the lecture. The lecture comprises straight and the coiled carbon tube. So we have seen the CNTs we have seen, and we have seen the type that it will be straight or it will be coiled. Coiled means it will go something like this. Straight means it will be the CNT will remain straight as it is. Again, it will be having some thickness. Then we can say it will be something like this. And same for the wall also. Sorry, for the coil also. How are the coiled CNT typically formed? So they are talking about this particular one, that by what process we form this. That is the option. We have to select the correct answer for this. Arc discharge, synthesis, chemical vapor deposition, oxidation in air, and none of the above. So you learn the answer in this in class that it will be the chemical vapor deposition technique, CVD. Okay, by arc discharge we can create the straight carbon nanotube. Okay, so with that we have got the answer B is the right answer for this question number 15. Let's move to the next question, question number 16. What defect in the tube wall can cause coiling in the CNT? Okay, so we are aware that we got one straight CNT. Now, what can cause this coiling to occur? It is a again it is a kind of defect. Now, what kind of defect is? Bend in the tube wall. B. Presence of the pentagons or heptagons instead of the hexagon. So instead of this, if pentagons are present or heptagons are present, so in that case, what will happen? The defects is these are the some kind of defect. Now we cannot fold down the we cannot keep the pentagon and heptagon in the plane. Okay, it is a certain type of defect, and due to this only the coiling in the CNTs we have observed. So this particular thing which we have learned, this coil, it is due. So in this particular case, we can see that the pentagons and the heptagons will be present. Okay, so the correct answer for this question will be the option B. Let's move to the next question. What defect in the tube wall can cause coiling in the CNTs? Oh, the same question. I made a mistake, I think. Again, the answer is B only. Okay, I repeated the question. Let's go with the 18, 19, and 20. Okay, three more questions I am having. Let's try to solve them. It's a match the pair following. Okay, A, B, C, D, E, 1, 2, 3, 4, and 5. So now the straight CNTs which we just discussed that it will be in the straight manner, and we have in the coil CNTs also. Now let's select the one of the most favorable answer pair for this straight CNT. A process used to release a noise and vibration. No, uh, carbon nanotube with a needle-like structure. Yeah, it is. Straight CNT is a carbon nanotube with a needle-like structure. So we can say that the A will go with the two. Coil CNT, a technique for synthesis. No, it is not a technique. A carbon nanotube with a curved or the wrinkled morphology. So B will go with the 4. Yeah, it is having the curved morphology. So B is matched with 4. Damping. Damping, we are aware that it can use to absorb the shock given to the material, any vibration given to the material. Okay, so we know that for the damping we can select a process used to reduce the noise and vibration. That is the correct answer. That's for C. We can go with the first one. So these three are over, and these three are over. So 3 and 5 are remaining now. Arc discharge synthesis. Okay, we have learned about this just now. That when to use it. It can be used a technique for synthesizing the carbon nanotube that result in the tube with the coil morphology. No, R discharge produce the straight morphology. So let's see the fifth option. Technique for synthesizing carbon nanotube that result in the straight tube. So D will match with the 5. And CVD process, we have known that it is used to produce the coil morphology. So E will match with the 3. So with that we have solved this pair and this is the right answer for that. Let me know if there is any doubt in this question number 18 in this math pair. Okay, since there is no, let's move to the next question, question number 19. Okay, so zeta is 0. Uh, yes, yes. Zeta is 0 is undamped. There is no damping involved in that. What will happen that it will just keep on oscillating. Okay, there is no damping over here. If zeta is less than 1, in that case what will happen? That will say that it is under damped, right? If zeta is greater than 1, it will be the over damped. And zeta is equals to 1, it means that it has somewhere between the over damped and the under damped. And it is a critically damped. So we can, okay, let's not put on the numbers and all. We are aware that, okay, how it is going to be affected. So that is was the question number 19 over here. Now we are having the one final question. Yeah, let me tell you that the same question has been like exactly same in a similar way. Our professor has also taught us. Okay, let's go to the next question, question number 20, the final one. This is quite interesting. Here we are having the three column. One specify the symbol, then quantity, what they are representing, and their corresponding SI unit. So we have to match. Let us say, let me mark them: A, B, C, D. 1, 2, 3, 4. I, double I. Okay. Now we need to mark accordingly. So B, what does B represent? Okay. So A, we are having B, we are having C, D. So A, B, C, and D. What do you think? What will be the A? Is it magnetic susceptibility, magnetic field density, magnetic field strength, or magnetization? So B, we are aware that B is a magnetic flux density. That is, it is option 2. H, we are aware that it is a magnetic field strength, that is externally applied strength, that is option 3. M is the magnetization, that is option number 4. And the K is a magnetic susceptibility, that is option number 1. Now, we have to mark their corresponding unit. That is B, which was the magnetic flux density. We need to mark what its unit will be. And that is nothing else, that is a Tesla. Okay, we represent the magnetic field strength as a Tesla, and we can call it with a Weber per meter square. Now H, that is the B1, that is magnetic field strength. Now this one is nothing but the amperes per meter. So this was second, and this will be the third one. Now C, that is magnetization. Magnetization, again, the unit of M and the unit of H is same. Okay, so we can say that again it will be the option number 3, ampere per meter. And D, that is a Susceptibility doesn't have any unit, so it will be the unitless, and the option is one. Okay. So with that, we have solved this question number 20. So let me know if there is any doubt in this particular question number 20. Okay. Since there is no, let me ask you that in this entire class that we in this entire week, in the lecture also, in the this dot solving session also, if you have any doubt, any question, please let me know. Please go ahead with any of the. Yeah, I'm just displaying the question. If you feel anything, let me know. Eight, seven, question number one is six, five. Okay, four, three. Question number one. These are the list of the concepts that we have learned. Okay, since there is no doubt, we can wind up this particular week seven. Okay, it was a great interaction with you all, and we'll meet again on the week eight. That will be our final lecture. Okay, so whatever doubt you guys might be having in the corresponding to the week eight or the entire course of the nanomaterial, we can discuss those things in the upcoming week. Okay, with that, we can wind up this particular lecture. Thank you all.